Unit 9, primitives. So with this we start integral calculus, which is in a sense like the mirror part of differential calculus. So in differential calculus we asked, what is the measure of how fast a function is increasing or decreasing, right? And that's the derivative. And further derivatives gives a sense of how this increase is increasing. Okay, so how this curvature of the function is changing. Okay, and we ended up with our Taylor expansions, with kind of put together all the information from many derivatives to tell a story about functions around certain points, right? Now, we can ask ourselves, well, if we have a function, right? We know that if we compute the derivative, we find another function, right? The derivative of that function. If we know the other function, can we go back to the original function? Okay, is there any operation like subtraction and addition, or multiplication and division? Is there an operation that allows us to go back to the original function? And that's what we call a primitive. Okay, so, and you may have heard this as indefinite integrals before. So this has a relationship with integrals, but I like to call them primitives, because so far we're not talking about integrals, which are kind of a type of sums. We'll deal with integrals in unit 10, right? But for now, we're talking about primitives. And so we say that a function capital F is a primitive of f, of small f, if the derivative of capital F is small f. Okay? So, and we denote this operation, the primitive of f is capital F. Okay? And this is the sign for the integral in general. So this is an S for the sum, okay, because integrals are sums. But this is kind of like the spoiler of the movie, because the relationship between primitives and integrals comes later. Okay, for now we just are worrying about if we have a function f, a function capital F, and then I go to f using the derivative, right? Then what's the operation that goes back? Okay, and this is the primitive. Okay. Now, in unit 7, we saw that if two functions, let's say function f and g, have the same derivative, right? Then they're similar, they're equal to each other except for a constant, right? That means that f is equal to g plus k, where k is a constant. Okay? So if you don't remember about this, review unit 7. Okay? That's one of the corollaries to the mean value theorem. So that means that the primitives to any function, right, are unique up to a constant, right? So if you have a function, if f is the primitive of f, small f, g can also be a primitive of small f and be different from f, but then the relationship between these two is that there is a constant that equals both of them, right? Now, because the primitives are like the opposite operation of the derivative, then that means that the primitives obey the same linear rules as the derivatives do. So, for instance, the primitive of this function af plus bg, and we say dx, which we'll see what this means when we get to integrals next unit. This is equal to a times the primitive of f plus b times the primitive of g. Okay, so this is capital F, this is capital G, for instance, right? And this is easy to see, right? So if af plus bg, we compute the derivative of this, then this is a derivative of f, b the derivative of g, but this is small f and this is small g. Okay, so you can see how we get from this to the other, right? Now, From this definition, seeing that the derivative is so the primitive is the inverse of the or the reverse of the derivative, then we can see many kind of elementary primitives, right, that you need to know by heart, right? So if we have x to the alpha when alpha is different than -1, then the primitive is x to the alpha plus 1 divided by alpha plus 1, and it's easy to see because if you differentiate this, you have x to the alpha, right, times alpha plus 1, and then divided by alpha plus 1 you get 1, right? So that's what you get. 1 over x, or x to the -1, the primitive of this is the logarithm of the absolute value of x, and because if you compute the derivative of the logarithm you get 1 over x, right? And the exponential is the same. A to the x is a to the x divided by the logarithm of x, because the derivative of a to the x is a to the x times the logarithm of a, right? Now the primitive of the sine is minus the cosine, because the derivative of the cosine is minus the sine. The primitive of the cosine is the sine, because the derivative of the sine is the cosine. The hyperbolic sine and the hyperbolic cosine are primitives of each other. And then these are two interesting ones. 1 over 1 plus x squared is the primitive of this is the arctangent, right? And 1 divided by the square root of 1 minus x squared, the primitive of this is the arcsine. Now the primitive of the tangent is 1 over the cosine squared, and the primitive of the hyperbolic tangent, it's the other way around, sorry. The primitive of 1 over the cosine squared of x is the tangent, and the primitive of 1 over the cosine, hyperbolic cosine squared is the tangent, hyperbolic tangent. Okay? So you need to know all of them.